In this video, I'm going to describe the Boyer-Moore-Horspool algorithm, with a worked example and a brief discussion of the algorithm's complexity. Boyer-Moore-Horspool is a very simple algorithm for solving the problem of string matching. That is, the problem of finding the first occurrence of a substring, called the pattern, within a larger string. This occurrence of the pattern in the string is called a match, and it can be represented as an offset from the beginning of the string. Before we look at Boyer-Moore-Horspool, I'm just going to describe the naive algorithm for this problem, because that will introduce some concepts that will be useful later on. The naive approach is to take every substring with the same length as the pattern, starting at the beginning, comparing it with the pattern, and if the comparison fails, trying again with the substring starting at the next character. You can think of this as trying to line up the pattern with the match, by repeatedly shifting the pattern to the right, like this. Each of these blue substrings that we try to match against is called a proposed match, with the final, successful match shown in red. The Boyer-Moore-Horspool algorithm is often able to shift by more characters at each iteration by looking at the character at the end of the proposed match and considering where it appears in the pattern. It stores this information in a table so that it only needs to be computed once. If the character at the end of the proposed match, call it C, is not in the pattern at all, then the match must start after C's position in the string, so the pattern can immediately be shifted right by its length. If C is in the pattern but the proposed match fails, then the pattern is shifted so that the rightmost occurrence of C in the pattern is aligned with the occurrence of C just found in the string, and the check is repeated. Of course, when we're looking for the rightmost occurrence of a character in the pattern, we ignore the last character, because if we didn't, we wouldn't be shifting the pattern at all, because the two characters would already be lined up. So here, although the last character in the pattern is C, at the end we instead shift so the C before that is aligned with the C just found in the string. Here's the algorithm in pseudocode. So for each character in the pattern except the last one, we make sure that the shift of that character is the distance of its last occurrence from the end of the pattern. The shift for the characters that aren't in the pattern is the full length of the pattern by default. We note what the last character in the pattern is, and we start at the beginning of the string. So here, I points to the end of the proposed match. Then, if the last character in the proposed match is the same as the last character in the pattern, we then check to see if the match succeeds and return the offset of the beginning of a successful match if so. Otherwise, we shift I by the value found in the table. So here's a worked example. Match the pattern BAB against the given string. The first step is to build the table containing the distance of each character from the end of the pattern. For B, the rightmost occurrence, ignoring the last character in the pattern, is at position 1, so the value for B is 3 minus 1, which is 2. For A, the rightmost occurrence is at position 2, so the distance from the end of the pattern is 1. For all other characters, delta is the length of the pattern, which is 3. And we start looking at the first possible match. So here, the character at the end of the proposed match is the same as the one at the end of the pattern. However, the proposed match fails, so we look up B in the table and shift right by 2. E is not the last character of the pattern, so we look it up in the table and shift right by 3. A is not the last character in the pattern, so we look up A and shift by 1. B is the last character in the pattern. The proposed match matches the pattern, so the algorithm returns the offset of the beginning of the match, which in this case is 7. So what's the complexity of the algorithm? Well, when we're comparing the proposed match with the pattern, the worst case is that we need to compare every character. If the length of the pattern is m, then this means that there are m comparisons in the worst case. The minimum distance that we can shift at each iteration is 1. So the largest possible number of iterations is the length of the string minus the length of the pattern. If the length of the string is n, then the worst case running time is big O of n times m, which is no better than the naive algorithm. For example, if the pattern were A, B, 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 and the string were a long string of B's, then the rightmost occurrence of B, ignoring the last character of the pattern, is a distance of 1 from the end of the pattern. So delta of B is 1, and we end up shifting by 1 each time. Because the mismatch is at the beginning of the proposed match, we make 4 comparisons when comparing the proposed match B, 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 B with the pattern. In practice, Boyer-Moore-Horspool does a lot better than the naive algorithm. In the best case, no character in the pattern appears in the string, so shifts are always the length of the pattern, and the comparison between shifts, between the strings, fails after 1 step. This leads to big O of n divided by n iterations, and because the comparison only takes 1 step, a runtime of big O of n over m. Clearly, the performance depends on how far the pattern can be shifted at each iteration, and for that reason, Boyer-Moore-Horspool tends to perform well on longer patterns and large alphabets, because of the larger shifts and the greater likelihood of mismatches early in the comparison, respectively. This table is from Horspool's original paper, and it compares the rate at which input strings are processed, depending on the pattern length, by 4 algorithms. The Boyer-Moore algorithm here is an earlier algorithm of which Horspool's is a simplification. This shows that the algorithm is particularly suitable for longer pattern lengths. Boyer-Moore-Horspool obviously requires some setup time. Initializing the entries in the shift table to the length of the pattern clearly takes a number of steps equal to the cardinality of the alphabet, and then adding the last occurrences takes big O of m time, where m is the pattern length. And clearly the size of the table is big O of the cardinality of the alphabet. So in summary, the steps of the algorithm are to build the shift table from the rightmost occurrences of characters in the pattern, ignoring the last character, then to try to match the pattern against the string, starting at the beginning of the string and starting each comparison at the end of the proposed match, and if the comparison fails, to shift the pattern by looking at the last character of the proposed match and finding its distance from the end of the pattern in the table. In terms of complexity, setting up the table means iterating over the alphabet and over the pattern. In the worst case, the time complexity of the loop is big O of n times m. The best case is big O of n over m, and in practice the algorithm is fast, especially for long patterns. So that's the Boyer-Moore-Horspool algorithm for string matching.